Hello and thanks for using TickBoom. For this video I'm focused on part 3 of this 5-part question, and it follows on directly from parts 1 and parts 2, which I worked through in 2 separate videos. So if you haven't already worked through those 2 videos, go and take a look, because the way this question has been written, each part builds very incrementally on the parts that came before, and we make use of the results that we've shown to help with the next part. So if you haven't worked through those, it would be, I think, very challenging to follow along with what I'm about to work through. So if you haven't already, take a look. If you have already watched those videos, stick around and I'll work through part 3. Now part 3 is asking us to prove that every n greater than or equal to 2 also satisfies 1 on cubed root of 1 plus 1 on cubed root of 2 plus all the way up to 1 on the cubed root of n, that sum being greater than or equal to the integral from 1 to n plus 1 on 1 on the cubed root of x dx. So we want to prove that, and from there we want to then deduce that x1 plus x2 all the way up to plus xn is greater than n minus 1 to the 2/3 on 2 for each n greater than or equal to 2. So at first glance this part 3 is very similar to part 2, the only difference being that the inequality this time has a greater than or equal to sign against our integral. So we're asking for something greater than an integral. So I think we're going to still use our charting technique, but this time we'll use rectangles that sit above the curve, not below. And then hopefully from there we can make use of what we've just shown and anything else earlier to then deduce what we're being asked to deduce. So the first part of this question is asking us to prove that 1 on the cubed root of 1, I'll just write that as 1 on 1 to the 3rd, plus 1 on 2 to the 3rd, plus all the way up to 1 on n to the 3rd. That's greater than or equal to the integral from 1 to the n plus 1, and it's 1 on cubed root of x. I'll just write that as x to the negative 1/3 dx. So that's what we want to prove. Again, just like I did in part 2, I'll start by drawing up a chart. So we go 1, 2, 3, 4, and this time notice our integral goes up to n plus 1. So we'll go to n and then n plus 1. Here we'll go, so we'll go 0.2, 0.4, 0.6, 0.8 and 1. Just like last time, I'll key in some figures to get the general shape of our curve. I know when we've got x is 1, we'll get 1 because 1 to the power of anything is 1. For the others, I'll just key 1 divided by 3. I'll store that. So we'll get 2 to the power of negative 1/3 is just under 0.8. 3 to the power of negative 1/3 is just under 0.7. 4 to the power of negative 1/3 is just over 0.6, and that's probably enough. I'll just connect those dots. And we know that the integral, just as it was in part 2, represents the shaded area under this curve. Now for our inequality, we're going to use rectangles again, but this time we'll draw our rectangles above the curve. And that way, when we get the area of our rectangles, we'll be able to see by inspection that that area will be greater than or equal to the area under the curve. And so that's the little trick with this one. It's just having the same technique generally, but this time thinking, well, if I'm dealing with a greater than or equal to inequality against my integral, I want rectangles above the curve. But from there, exact same technique. So by inspection we can see the area under the rectangles will be greater than or equal to the area under the curve. area under the rectangles, it'll be 1 on 1 to the third times 1 plus 1 on 2 to the third times 1. Each of these has a width of 1 plus all the way up to 1 on n to the third times 1. That's going to be greater than or equal to the area under the curve is represented by the integral. It's very simple. All these times 1s can disappear, so it's 1 on 1 to the third plus 1 on 2 to the third plus all the way up to 1 on n to the third is greater than or equal to the integral from 1 to n plus 1 x to the negative a third dx. So again, very straightforward. Once you've got the chart drawn up in the necessary way, it becomes a very simple thing to prove what we're being asked to prove. So now on to the next part of this question, which I'll do over the page, which is asking us to deduce that x1 plus x2 plus all the way up to xn, that's greater than n minus 1 to the 2/3 on 2. So that's what we want to deduce, and that's for n greater than or equal to 2. Now, this greater than sign makes me think that the result we proved in part 2, that result of xn plus 1 is greater than 1 on 3 to the cubed root of n minus 1, that result I think will come in handy for two reasons. First of all, it's got the greater than sign. And secondly, it's quite clear that the people who wrote this question, this very well written question, have made it so that each part builds upon what's been proved in the earlier parts. So it's kind of a hint that if we just prove this in part 2, the reason we were asked to do that is to help us now in part 3. So for those two reasons, that's why I think this is a good place to start. So what I'll do is I'll start writing out some of our x's. So we know x1 is equal to 1, that's just part of the recursion. And I should say this is for n greater than or equal to 2 as well. X2 is also equal to 1, very easy to demonstrate, 1 on 1 squared is 1. X3, which is 2 plus 1, so the very first time we can use this inequality, is greater than 1 on 3, and it'll be the cubed root of 2 minus 1, which is 1, so 1 to the third. And that's because x3 is x2 plus 1, so in this case n is 2, 2 minus 1 is 1. X4 will be greater than 1 on 3 times, so for x4 n is 3, 3 minus 1 is 2, so it'll be 2 to the third. And all the way up to xn will be greater than 1 on 3 times, and in this case, if it's n, xn plus 1 is effectively inserting in there n minus 1 to get xn, so it'll be 3 times the cubed root of n minus 1 minus 1, or n minus 2 to the third. Very easy to get caught up there and kind of get that wrong, so you need to be careful and cautious, but fundamentally we're just inserting different values of n for this inequality. Now, given all that, we can write out x1 plus x2 plus all the way up to xn. We know that's going to be greater than, well, 1 plus 1 plus 1 on 3 times 1 to the third plus 1 on 3 times 2 to the third plus all the way up to 1 on 3 times n minus 2 to the third. So that's going to be greater than 1 plus a third times 1 on 1 to the third plus 1 on 2 to the third plus all the way up to 1 on n minus 2 to the third. And hopefully this looks familiar because it's very similar to what we've just proven, being 1 on 1 to the third plus 1 on 2 to the third, always all the way up to 1 on n to the third, is greater than or equal to this integral. So let's just work out that integral. So we're going to be looking at the integral from 1. Now if we're going up to n minus 2 here, and this went up to n, and this was n plus 1. So if I insert n minus 2 into there, I get n minus 2 plus 1 is n minus 1. So the integral I care about goes up to n minus 1 of x to the negative a third dx. So let's just evaluate that, which is equal to, so negative a third plus 1 is 2/3, so x to the 2/3 on 2 on 3, between 1 and n minus 1, and that's equal to, bring out the 3 on 2, n minus 1 to the 2 on 3 minus 1. So that's going to come in handy later. So effectively, if what we're summing is greater than all of this, then, and this is greater than or equal to that, then what we're summing must be also greater than that. So we'll get greater than 1 plus 1 plus 1 on 3 times 3 on 2, n minus 1 to the 2 on 3 minus 1. And now we just need to simplify this and see if we get to what we're looking for. So that's going to be, these 3's can cancel, so we'll go greater than 1 plus 1 plus a half, and I'll just expand this now. So we'll go a half n minus 1 to the 2 on 3 minus a half, which means it's greater than n minus 1 to the 2 on 3 on 2. 1 plus 1 is 2 minus a half, so plus 3 on 2. Now if this sum is greater than this plus something, it must also be greater than this by itself. So greater than n minus 1 to the 2 on 3 on 2, which is what we were being asked to show. So there we see, by doing the first part of this question using our charting technique, getting a result, and then making use of both that result and the result from part 2, we've been able to demonstrate this inequality that we've been asked to demonstrate. So there you see this question. It really is just building very incrementally. It's a very well written question, and that should be no surprise given it was written by the medalists of the Math Olympiad. But it really is a very interesting question to work through, because if you step back and look at the kind of techniques that I've had to use so far, apart from induction in part 1, the rest of it is really just algebra. I mean, we've had to kind of go back to first principles almost in thinking about what is an integral, and it's the area under a curve, and the idea of rectangles and being relative to that curve. But again, once you get there, the area of the rectangle, very simple. All of this is just algebra. You need to be careful not to make mistakes, but it's actually a very well written question because it's both very difficult but also very simple at the same time. So hopefully you've been able to follow along up to this point. So that's part 3 all done. So in the next video I'll move on to part 4, which at the time of recording is the last part of this question I've been able to work out. So I'll see you then in that next video, and tick boom.